In this video, I will once again show you guys how to show that these three functions are linearly independent, the Li right here. In the previous video, I showed you guys that's the same exact three functions. They are linearly independent by using the definition, which is C1, C2, C3, right? And we saw that C1, C2, C3, they all had to be 0 in order to make that equation 0, isn't it? Well, here's another way to do it. And this way only works if you want to show something that's linearly independent, okay? Once again, this following way, it only works if you want to show three random functions to be general, okay? Three functions to be linearly independent. And this is the name for it. We are going to use what we call the Wronskian, all right? And here's the notation for that. W, and sometimes you can put a bracket with big parentheses, up to you. And let me put down the three function versions right here. We have y1, y2, y3, all right? So this is a notation. It's called the Wronskian, and what you do is, on the right-hand side, it's actually a determinant. So det, a determinant of a 3 by 3 matrix. So I'll draw the matrix right here. And the matrix are going to be, the first row are just the original functions. y1, y2, y3. And the second row are going to be the first derivative. And then the third row are just going to be the second derivatives. So here, this is y1 prime, y2 prime, and y3 prime. And then the last row is y1 double prime, y2 double prime, and then y3 double prime. And you are going to work out this determinant of this 3 by 3 matrix. At the end, if you can show that this right here is not always, okay, or you can also interpret this as, you want to show this is not identically equal to. That's why I put on the triple line right here. You want to show this is not always, this is not always not equal to 0. This is not identically equal to 0. From here, if you can show this, it's not identically 0, you can say that the functions are Li, linearly independent. However, if you do end up this determinant to be 0, you cannot say the functions are linearly dependent. Most likely they are, but you cannot use that as an argument, all right? If there's a request, I'll do that video for you guys. But at the moment, this is what you have to remember. To show Li, you can just go ahead and use the Wronskian. Hopefully, this is not identically equal to 0. In that case, you are done. If it's equal to 0, technically, you have to do more work. You have to go back to the definition, all right? Well, to show LD, you must use the definition, the C1, C2, whatever. Anyways, here we go. Let me just put this in action for you guys. I'm going to find the Wronskian for these functions. So I put on y1, y2, y3, all right? Which is going to be a determinant of a 3 by 3 matrix, which the first function is 2t minus 1, and then the second function is t squared plus 5. The third one is 4t minus 7, like this. And differentiate this right here. This is going to give me 2. And I will do it again, which is going to be 0. And I'll see that this is 2t, and then differentiate that again, which is 2. This right here, derivative is 4 and then 0, right? This is my t, by the way. Okay, so how can we calculate the determinant right here? One way to do it, when we have a 3 by 3 matrix, is that we can just copy the first two columns. And let me just write the t better right here for you guys. We can just copy down the first two columns on the side here, and I'll put this down as 2t minus 1, and then 2 and then 0. And I'll copy this down right here as well. T squared plus 5, 2t, and then 2. Okay? And this is what we're going to do. We're going to multiply this way for the diagonals, right? So we do this times this times this times that. So is you do this kind of product like this, and then you add them along the way, okay? And after you finish all that, you do backwards these diagonals. And when you do that, you subtract. And when you do this, technically they are still adding, but you are going to be subtracting the whole thing. So you can look at it as adding, you can look at this as subtract the whole sum, or you can just think about subtract, 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 up to you. Anyways, let's get going on this. So first of all, I will just do this times that. Well, 2t minus 1 times 2t, and then times 0 is just 0. So the first term, right, the first error right here is just 0. Next, I'll do this times that. Once again, well, this times 0, so it's still plus 0, isn't it? It's kind of suspicious because I have a lot of 0, but just check this out. Next, I'll do this times that. So I will have to actually put down some work now, right? Parentheses 4t minus 7 times this 2 times that 2. All right? And now I will be subtracting, and then just put it down here. I'll put down a big parentheses, and I'll do this diagonals right here. This way, all right? Of course, you can do this way, this way, this way. Doesn't matter. But let me just go back. Anyways, this times this is 0. And then you do this times that. I have to put down the work now. Put on plus because I have the negative on the outside with the parentheses. So we have 2t minus 1 times 4 times 2. Like this, right? And then at the end, we'll do this times that, which is once again 0, and that's wonderful. Okay, so 0, 0, don't matter. And this is 4, right? 2 times 2 is 4. Times 4t is 16t. 4 times negative 7 is minus 28. And then let me put down the minus right here. Okay, so I have to worry about this term. Check this out. 4 times 2 is 8. 8 times 2t is, and then 8 times minus 1 is minus 8, like that. Okay, so what do we end up with? You distribute, you get, and then you distribute, you get plus 8, right? So 16t minus 8t is, and you see that negative 28 plus 8 is minus 20. This is the determinant of this 3×3 matrix. Namely, this is the Wronskian for these three functions. Just indicate that this is not identically equal to 0. You're good. This is great. Therefore, this is the work that you do. At the end, you can say that y1, y2, y3 are linearly independent by using the Wronskian. One last time. To show functions are Li, you can use the Wronskian. But to show functions are LD, use the definition. That's it.